Most people treat backpropagation as a black box. You call loss, backward, and gradients appear. But there is no magic here, just one rule, applied node by node, from the loss all the way back to every weight in your network. That rule is the chain rule. Today we are going to build backprop from scratch, follow a gradient through every layer of a real two-layer network, understand why deep networks with sigmoid activations fail to train, and understand why residual connections solve that problem. By the end, loss, backward, will be completely transparent to you. The chain rule has three forms you need to know. Form 1, scalar chain rule. If y equals f of g of x, then dy over dx equals f prime of g of x times g prime of x, outer derivative times inner derivative. Form 2, multivariable chain rule. If a variable feeds into an output through multiple paths, the total derivative is the sum over all paths of the product of local derivatives along each path. This is the sum of paths rule. Every neuron that receives gradient from multiple downstream sources sums those contributions. Form 3, vector and matrix chain rule. If y equals f of x where both are vectors, the chain rule becomes dl over dx equals the Jacobian of f transposed, times dl over dy. For a linear layer z equals w times x, the Jacobian is w itself, so the gradient flowing back through the layer is w transpose times the upstream gradient. Let us build backprop by hand through a two-layer binary classification network. Forward pass, x goes through w1 times x plus b1, then relu, then w2 times a1 plus b2, then sigmoid, then binary cross-entropy loss. 4 backward steps in reverse. Step 4, gradient of BCE with respect to sigmoid output A2. This is A2 minus y divided by A2 times 1 minus A2. Step 3, gradient of sigmoid node. Sigmoid prime is A2 times 1 minus A2. These two multiply and cancel completely. The gradient of BCE plus sigmoid is just A2 minus y. This is why PyTorch recommends BCE with log its loss, fused sigmoid, and BCE is numerically stable and the gradient is trivially clean. Step 2, linear layer W2. Gradient of L with respect to W2 is the upstream delta, outer producted with A1. This is the matrix calculus chain rule. Local Jacobian is A1 transpose. Step 1, ReLU layer. Gradient is the upstream gradient, masked elementwise by which neurons were active in the forward pass. Dead neurons, those where Z1 was negative, pass zero gradient backward. This is the dead neuron problem in ReLU networks. PyTorch AutoGrad automates everything we just did. During the forward pass, every operation creates a node in the computation graph. Each node stores a grad_fn, a backward function, and the tensors it will need to compute its local gradient. L grad_fn points to BCE loss, which points to sigmoid backward, which points to backward for the W2 times A1 operation, and so on. When you call L backward, PyTorch walks this graph in reverse topological order, calling each grad_fn with the upstream gradient, computing the local gradient, and accumulating the result into the leaf tensor's grad attribute. 3 things to remember. 1. Call optimizer 0_grad before every backward pass, otherwise gradients accumulate. 2. Use torch.no_grad. During inference, it disables graph construction, saving memory and time. 3. Gradient checkpointing trades compute for memory by not storing intermediate activations. It recomputes them during the backward pass. This allows training with much larger batches. Two gradient pathologies, both explained entirely by the chain rule. Vanishing gradients. Sigmoid prime is at most 0.25. After 10 sigmoid layers, the gradient has been multiplied by at most 0.25 to the 10th, which is less than 10 to the minus 6. Early layers receive essentially zero gradient and stop learning. The fix is ReLU. For active neurons, ReLU prime is exactly 1, so multiplying by it does not shrink the gradient. Residual connections add a skip path. The output equals f of x plus x, so the gradient is f prime of x plus 1. The plus 1 guarantees there is always at least one path with gradient magnitude 1, regardless of what f prime is. This is why ResNets can have hundreds of layers. Exploding gradients. If the weight matrix has spectral norm greater than 1, the Jacobian product grows exponentially with depth. In RNNs this becomes catastrophic for long sequences. The fix is gradient clipping. If the gradient norm exceeds a threshold, scale the entire gradient vector down to that threshold. This is used in virtually every large language model training run. 4 things to know cold. 1. The chain rule is multiplication of local derivatives along each path, summed over all paths. 2. Computation graph stores the forward pass and backward functions at each node. 3. Vanishing gradients come from products of numbers less than 1, fixed by ReLU, residual connections, and He initialization. 4. Exploding gradients come from products of numbers greater than 1, fixed by gradient clipping and batch norm. Exercise. Implement a 2-layer network in pure NumPy, compute all gradients by hand, then verify against PyTorch AutoGrad. Maximum relative error should be under 1e5. You now understand the complete mechanism of backpropagation. Not as a mysterious algorithm, as the chain rule applied recursively on a directed acyclic graph. Every gradient flow problem you will ever debug traces back to either a vanishing or exploding product of local derivatives along some path in that graph. Video 21 is the optimization landscape. Given that we can compute gradients, what do we do with them? Why does gradient descent find good solutions even though neural network loss surfaces are non-convex? Why do saddle points matter more than local minima? Subscribe so video 21 is ready. Post your answer. Why does a residual connection guarantee gradients do not vanish? See you in video 21.